Welcome back to Chem Exam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at Cape Chemistry Unit 1, 2021, Module 3, Chemistry of the Elements. Let's go. Number 3. The group 2 elements and the first row transition elements exhibit certain similarities and distinct differences in their physical and chemical properties. Table 2 provides information on the first ionization energy, i.e., atomic radii, AR, electronic structure, ES, of atom and oxidation numbers /state, OS, for some of the elements. So let's examine the table. Here we have a list of elements: magnesium, calcium, strontium, vanadium, chromium, manganese, iron, and cobalt. So let's start by filling in the blank spaces for the electronic structure and look at the oxidation state for each element. Magnesium, let's start with magnesium. 12. So we need 1s2, 2s2, 2p6, 3s2. These electrons here would have the highest energy, therefore they will be lost before the other electrons, giving it a +2 charge. To write the simplified version, we're going to call this neon because it has an atomic number of 10. So for magnesium, the simplified version is neon 3s2, or you could write out the entire configuration. For calcium, it is 20 for the atomic number. So we go 1s2, 2s2, 2p6, then 3s2, 3p6, then 4s2. So this part represents argon, which is 18. So you lose these 2 electrons, which has the highest energy, and therefore you get a +2 charge. For strontium, the atomic number is 38. So we'll start with 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, and 5s2. Now, if you count up all the electrons from 1s2 to 4p6, you get 36 for krypton. So that's 36. So these 2 electrons would have the highest energy. So when you lose these 2 electrons, of course, you form a +2 charge. For vanadium, the configuration is 23. So we need 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d3. And this is the configuration for argon, which is 18. So you could write the shortened form of the electronic configuration, which is argon 4s2, 3d3. Now remember, you could write 3d3, then 4s2. It's also okay to write 4s2, then 3d3. Why? Because when the 4s orbitals are empty, they are lower in energy than the 3d orbitals. However, once they are occupied, they move above the 3d orbitals, having higher energy. So both ways are accepted. Now, if you look at this, you could lose the 2 electrons, giving vanadium a 2+ charge, or you could lose 2 from the S and 1 from the d orbital, giving you a +3 charge. For chromium, you would recall that we've discussed in previous questions that chromium is an anomaly. So we would not fill the 4s orbital with 2 electrons first, because that would make it unstable. For it to be stable, you need a partially filled d orbital. In order to acquire that, the s orbital, the 4s orbital, must have 1 electron, so that the other d orbitals will be partially filled. And that is what makes it stable. Now, for chromium, you could lose 1 from the s and 2 from the d orbitals, or 1 from the s and all 5 from the d orbitals, giving you +3 and +6. For manganese, the atomic number is 25. So we could go AR, which is 18. So you could write out from 1s2 to 3p6, which is 18. And then 4s2, and then 3d. And remember, if this is 18, that's 19, 20. So you need 5 more electrons. So you have 3d5, 4s2 here. And the most prevalent ions for manganese is +2, where you lose the 2 electrons from the s orbital, or you could lose all 5 from the d along with the s to give you +7. Iron would carry an atomic number of 26. So iron would carry an atomic number of 26. So that again would carry us 18 for argon, 4s2, that's 20, and so we need 3d6. And the most prevalent ion for iron is +2 and +3, where you lose 2 from the s orbital, or 2 from the s orbital plus 1 from the d orbital. And cobalt would carry an oxidation state of 27. So that would be Ar with 18, 4s2, that's 20, 3d7. That's 27. Again, the most prevalent ion for cobalt would be 2 from the s orbital, or 2 from the s orbital plus 1 from the d orbital. 3 part 2. Explain the difference between the trend of the first ionization energy for the group 2 elements and the first row transition elements. So for the group 2 elements, they have larger atomic radii, smaller nuclear charge, therefore lower ionization energy. Or I can say lower first ionization energy. While for the transition elements, they have smaller atomic radii and larger nuclear charge, therefore higher first ionization energy. Now, the nuclear charge is a charge of the nucleus. So the more protons you have, the more positively charged your nucleus would be to attract the electrons on the valence shell. Part B1. Account for the difference in oxidation state between vanadium and calcium. So if you look at calcium, let's look at calcium first. We will write the configuration for Ar 18 plus 4s2, which you saw earlier. Therefore, we'll only lose 2 electrons from the 4s electrons, giving it a +2 oxidation state. Note the d orbitals are empty. But for vanadium, which carries 23, we have 18 plus 2 for the 4s orbitals. 4s orbitals, so this is 4s2. That's 20 plus 3, so we have 3 in the d orbital. So you'll notice now that we can lose 2 electrons from the 4s orbital, Or we can lose 2 from the 4s and 3 from the d orbital. Or 2 from the 4s and 1 from the d orbital to give us a +3 charge. We could continue to lose 2 from the 4s and 2 from the d orbital to get a +4 oxidation state, or 2 from the 4s orbital and 3 from the d orbital to give us a +5 oxidation state. So that explains the difference in oxidation state between vanadium and calcium. However, the most prevalent ions would be +2 and +3. B part 2. Comment on the following. Calcium carbonate is more thermally stable than magnesium carbonate. So if you look at magnesium carbonate, you'll see that we have a positively charged magnesium, which has a small atomic radius. It will then combine with the carbonate ion, which is of a larger size. So when you have a small, highly charged element with a large anion, then what you'll have is distortion or polarization, because the 2+ will be attracting the anion, giving it a distorted shape, making it easier to break. When you compare that with calcium, which is larger than magnesium, so the sizes of the calcium 2+ ion and the carbonate 2- ion are comparable. So less distortion or less polarization, hence making it more stable and harder to break. C part 1. Explain the following observation in terms of the stability constant of the complex ion formed when concentrated HCl is added to a pink solution of cobalt 2 chloride. The solution turns blue. So what you should know is that complexes have different colors, and this is a property of transition elements, a chemical property. Now, this is our complex, which is hexa aqua cobalt 2+ ion. And when you react it with HCl, and the Cl- comes from HCl, the Cl- will displace the water because it is this ligand. Cl- is considered a ligand, and it is more stable than water. Hence, it forms a more stable complex than with water. And once you replace the water, my tetrachlorocobaltate 2 ion becomes blue. So I move from pink to blue. So all the water was displaced. So the Cl- has a higher stability constant than water, therefore forms a more stable complex. Cl- ligand is larger than water, therefore forms a tetrahedral complex and not octahedral. And of course, a tetrahedral complex is more stable than the octahedral complex. And that is why you form the more stable complex here. Part 2. Write a balance equation for the reaction in C1. Well, to explain what is happening here, I already wrote out the equation for you, so we could just put it back right here. So what do we have? We have hexa aqua cobalt 2 ion. Now you say cobalt 2 because the charge on the complex is positive. But once the charge on the complex becomes negative, the name would change to add ATE at the end. So it would be tetrachlorocobaltate 2 ion. And this represents the equation for the process taking place. We call this ligand exchange. Part D. Ammonium vanadate, NH4VO3, is an orange solid. Tests are performed on ammonium vanadate and certain color changes are observed. Complete table 3 below to show the observation expected for each of the tests. So this is our test in table 3 on ammonium vanadate. So the test is a few cm cube of 3 molar sodium hydroxide is added to a small amount of solid ammonium vanadate, followed by a few centimeters cube of 3 molar sulfuric acid. So in looking at the test on ammonium vanadate, you see that it is an orange solid. Now, once it is mixed, you now form a solution of dioxovanadium 5, which is yellow in color. When the few pieces of granulated zinc are added to the solution, you are going to have reduction. Now, reduction means that the oxidation state on the V will move from +5 to a lower number. So what's going to happen here is when the zinc is added to the dioxovanadium 5, it is reduced to oxovanadium 4, which is blue in color. While the change is taking place, you have two colors mixing, yellow and blue, which forms green. So what you should observe here is a green color as the dioxovanadium 5 is reduced to oxovanadium 4, which is blue. So the blue and the yellow mix to form green. The zinc will cause the complete reduction of the dioxovanadium 5 to oxovanadium 4, and that is when you observe a blue color. Further reduction will cause the oxovanadium 4 to be reduced to vanadium 3+. And again, further reduction with the zinc will carry the vanadium 3+ to vanadium 2+, which is violet in color, or lilac or lavender. So we go from dioxovanadium 5, which is yellow, to a mixture of yellow and blue as the zinc is reducing the dioxovanadium 5 to oxovanadium 4. That mixture gives you green. Once the reduction is complete, you now have blue oxovanadium 4 all by itself. The zinc will cause further reduction from oxovanadium 4 to vanadium 3 and further reduction to vanadium 2+. Vanadium 3 is green and vanadium 2+ is violet or lilac or lavender. So you are to write the formula of the species formed, which is responsible for each of the color change observed in D. So again, it's the same thing we're looking at here. So our colors and formula species would go from yellow, which is dioxovanadium 5, to a mixture of yellow dioxovanadium 5 and blue oxovanadium 4, which forms green when they are mixed, to the complete reduction of the dioxovanadium 5 to only oxovanadium 4, that would be blue, and then further reduction would carry the oxovanadium 4 to vanadium 3, which is green in color. Again, more reduction by the zinc would carry the vanadium 3+ to vanadium 2+, which is violet or lilac or lavender in color. This is the end of Module 3, 2021. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.